Enthalpy changes in solution. Although you may think to dissolve ionic crystals in water, you need a large amount of energy to break up the crystal lattice and to overcome the strong attraction forces between ionic crystals. But the fact is that you actually can dissolve ionic salt, such as sodium chloride, in cold water. So how did this happen? If you looked at the enthalpy change of solution for dissolving 1 mole of sodium chloride, you will find it has a very small positive value, approximately 4 kilojoules per mole. Another example is the enthalpy change of solution for magnesium chloride. It is equal to minus 55 kilojoules per mole. It has even a negative value, which means it is an exothermic process. So first we need to know what do we mean by enthalpy change of solution, delta H solution. The enthalpy change of solution, delta H solution, is the energy absorbed or released when 1 mole of ionic solid dissolves in a sufficient amount of water to form a very dilute solution. If we looked back at the lattice energy of sodium chloride, or the energy released from forming the sodium chloride crystals, it is equal to 788 kilojoules per mole. Remember, this is a released energy, which has a negative value. So you would assume that breaking sodium crystals would require to absorb the same amount of energy, which is equal to 788 kilojoules per mole. But from the equation you can see that you need only 4 kilojoules per mole. So where does the energy needed to separate the ions come from? When you try to dissolve lattice crystals of sodium chloride in aqueous solution, in the first step, the bonds between ions are weakened due to the attraction between the positive ions, sodium, with the oxygen of water molecules, and the negative ions, which is chlorine ions, with positive hydrogens of water molecules. So you have two processes happening at the same time. Energy is absorbed to break down the bond between the crystal lattice, and the energy is released due to the formation of a coordination bond between ions of the crystal lattice and water molecules. We call the second step the enthalpy change of hydration. The enthalpy change of hydration has always a negative value, and this value is larger, more negative, when the ionic radius is small for ions with the same charge. For example, lithium is more exothermic than sodium because lithium has a smaller ionic radius. For ions with different charges, the larger the charge on the ions, the more exothermic it is. For example, magnesium ion is more exothermic than lithium ion because it has more charge on its ion. This enthalpy change of hydration releases energy sufficient to compensate for the energy needed to separate the ions in the crystal lattice. Let's construct the enthalpy cycle using Hess law. The enthalpy change of hydration for sodium chloride is equal to minus 784 kilojoules per mole, and the lattice enthalpy is equal to minus 788 kilojoules per mole. If the enthalpy change of solution is equal to the enthalpy change of hydration minus the lattice enthalpy of crystal lattice, this means the enthalpy change of solution, delta H solution, is equal to minus 784 kilojoules per mole for the delta H hydration minus the minus 788 kilojoules per mole for the lattice enthalpy would be equal to 4 kilojoules per mole. You can see that we needed only 4 kilojoules per mole in order to dissolve sodium chloride in water. This energy can come from the surrounding. That is why when you dissolve sodium salt in water, the container gets a little bit colder, because the energy needed is absorbed from the surrounding. Here is the energy diagram for the process. The lattice energy released during the formation of the crystal lattice is equal to minus 788 kilojoules per mole, and the hydration energy for both sodium and chlorine ions is equal to minus 784 kilojoules per mole. The difference between the enthalpy change of hydration and the lattice enthalpy, which is the enthalpy change of solution, is equal to 4 kilojoules per mole.